Hi everyone, and welcome to the video lecture series of Math 23. Today's lesson is entitled Surface Integrals of Vector Fields. So before we formally begin the discussion of surface integrals of vector fields, let us first look at something that will serve as the motivation for the construction of such integrals. So here we'll be talking about flux. So flux in general is the flow of energy through a medium or surface. In vector calculus, when we say the flux of a fluid across a surface, we are then referring to the amount in volume of that fluid that flows across, either in or out of the surface per unit time. Flux here is a scalar quantity. So here we have a fluid and a surface, and the motion of the fluid is captured by its velocity, and it's modeled by a vector field. So question is, if you are given a fluid having velocity field F and the equation of our surface S, of course we want to compute for the flux of F across that surface S. And we'll be doing that by constructing an integral. So our lesson for today will basically have two parts. First, we shall look on how we can orient a surface using its normal vector, specifically the unit normal vector. Then we shall proceed to construct an integral that corresponds to the flux that we want to solve. Okay, so a surface is said to be orientable if we are able to determine which is the outside and the inside of that surface. So we have two sides basically. The outside is where the outward normal vectors are all pointing, just like in this case. And the inside would be where all the inward normal vectors are pointing, or the negative of these vectors here. So on your right, we have the surface called the movie strip, and this is an example of a non-orientable surface because it only has one side. Okay, so again, we can use the unit normal vector of a surface to give our surface an orientation. So we'll have two cases. First, in the case that S has the Cartesian equation, for example, z equal to the function g of xy. So we can easily find the normal vectors to this equation or to this surface via the use of gradient. That is, we just write this one as z minus g of xy equal to 0, and we treat the left hand side as a function of three variables, and we just get its gradient. So the normal vector would just be negative g sub x, negative g sub y, 1. And to make it a unit normal, we just divide it by its corresponding norm. So all of these vectors are pointing upwards because of the third component, which is 1. Similarly, the negative of these vectors here are still normal to the surface, but they are now pointing downwards. So we just multiply this one by negative 1. So in this case, for an open surface, as a convention, unless stated otherwise, when we say that the surface, open surface, is positively oriented, we mean that its unit normal vectors are all pointing upwards. So positive orientation meaning the unit vectors are all upwards. That is for a open surface. Next, in the case that the surface is a parametric surface, so S here is parameterized using two parameters, in this case u and v, we can again obtain the unit normal vectors using the partial derivatives of u, of r rather, with respect to u and v, and getting the cross product. So either we use ru cross rv and divide it by its corresponding norm, or we use rv cross ru, or the negative of this one, still over the same norm. So the positive orientation should be consistent with the right-hand rule. What does it mean? So for example, you have this surface here. If you take a point, specific point on that surface, for example, if on that point r sub u is I hat and r sub v is j hat, then obviously ru cross rv, I hat cross j hat would give us k hat, which is pointing away from the center or upwards. So in that sense, RU cross RV would give us the positive orientation. But on some cases, for example, you have a point, but At that point, r sub u is j hat and r sub v is I hat. So to get an outward vector, a k hat, instead of using ru cross rv, I have to use rv cross ru. Okay. So another convention in surfaces, in orienting surfaces rather, is that whenever you have a closed surface, for example, a sphere, its positive orientation is when the unit vectors are all pointing outwards. So if it's open, positive orientation usually pointing upwards. But if it's closed, regardless uh, if the unit normal vectors are pointing upwards or downwards, what we want is the unit normal vectors to be pointing outwards or away from the center. Okay, so next is an example wherein we want to find the unit normal vector to this unit sphere S, parameterized as such: sine u cosine v, sine u sine v, and cosine u, with u having values from 0 to pi and v running from 0 until 2 pi. So we want the normal vector of this unit sphere that gives us the positive orientation. So we want the normal vectors to be pointing away from the center of our sphere. So to do that, I'll get r sub u and r sub v. So we can easily find r sub u. Okay, r sub u is cosine u cosine v. Okay, cosine u sine v. Okay, and negative sine u, right? And r sub v would just be negative sine u sine v, sine u cosine v, and you have 0. Then hopefully, if I get ru cross rv, it will give me the orientation that I want. So get the cross product between ru cross rv. So here, verify that ru cross rv is indeed the vector having components sine squared u, cosine v, sine squared u sine v, and sine u cosine u. Then to normalize this, I'll get its norm. So norm of that. And you can see by simplification that the norm is equal to the absolute value of sine u. But notice that u only varies from 0 to pi, meaning values of u is just on the first and second quadrant. Thus, sine u is always non-negative. And in this case, the absolute value of sine u would just be simply sine u. And then we can then compute for the unit normal vector. It's ru cross rv over norm, or it's negative. So hence, we can get the normal vector ru cross rv over this one to be given by this one. So notice that by inspection that these vectors here are pointing away from the origin. Why? Because simply n and r are the same vectors. So they're the same vectors. So they're pointing away from the origin or pointing outwards. So I know that I got the correct orientation or the correct normal vectors that would give us the positive orientation of S. Another way of checking whether you have the right orientation is to get a particular point, a test point. So, for example, we can get the point wherein u and v are both 0. So, u and v are both 0. And that corresponds to the point 0, 0, 1, or the north pole or the topmost part of our sphere. And on that point, the unit vector is again 0, 0, 1. And obviously, that vector points upwards, which in this case gives us the positive orientation test. So indeed, in this case, what we want for the positive orientation would be ru cross rv. So here's the sphere, and these are the unit normal vectors of our sphere. Okay, next. So to demonstrate the intuitive notion of flux and see its basic formula for example, constant forces and flat surfaces, we can consider the following system. So we have here the sun that gives out energy in the form of heat towards the earth. So we have here the earth. And let us assume that the force coming from the sun towards the earth are all going in a horizontal manner. So from right to left, all horizontal. So on the left we have earth, and we have some regions on earth, North Pole, somewhere in the equator, and somewhere below it. And let's consider, or let's assume that these regions here are all flat for simplicity. So let's look at first region A. So region A lies on the North Pole. So since the sun's rays are all horizontal, no heat penetrates this region. So the sun rays all just pass along the region but not across it or through it. And in that sense, the flux across or through A would be zero. And notice that at this region A here, the unit normal vector at A would be pointing downward. Sorry, on this scenario, we shall take the positive orientation to be the one wherein the unit normal vectors are pointing towards the Earth's core. So at region A, we have the normal vectors to be pointing downwards, whereas the force is horizontal. So this two, the normal and the force, has a theta of 90 degrees, and it makes zero flux across A. Then at B, we have region B, somewhere in the equator, on the rightmost part of the Earth. We expect that at B, we receive the most amount of heat coming from the sun because of its position. And notice that here at B, we have the unit vector to be going to the left, which is on the same direction as our force coming from the sun. So the unit normal vector and the force would make an angle of 0 degrees. And we expect that the flux here would be at maximum. Okay, then we look at this region C here. So at region C, we see that C still receives some heat from the sun, but not as much as B, and of course non-zero as compared with A. So if we think of this box here or this parallelepiped as the amount of heat absorbed by region C, then we can compute the said volume using the properties of our dot product. So we have the force, which is horizontal. Then we assume that C is a flat surface, flat region. Then we have its normal vector, and we make an angle theta across it. Then by the properties of our dot product and norm, the flux here or the volume of this parallelepiped will be given by this. F dotted with N, F is our force, N is the normal vector on the surface, and we have delta A to be the area of our base, or in this case, the area of region C. So that would be the flux at C. So such formula will be used when constructing our surface integral, or the integral that we'll be using to solve for the total flux across the surface. So note that this formula works for a flat surface. Okay. Now, we're ready to construct the integral that gives us the flux. So we begin by having an orientable surface S and F to be a continuous velocity field that is flowing across S. So we have F and we have the surface. So just like with any construction of an integral, we first subdivide the surface into small patches. Let's call the small patches S sub i's, and the area of each patch would be delta sigma sub I. So we approximate the patches by a plane. So instead of a curve, a curved surface, we assume that the small patches would be planar. Okay, next, since the patches are assumed to be very small, we can assume then that the velocity across each patch would be constant. So we just take a point on each patch and evaluate f at that point. Next, so using the formula from the previous slide, the flux across each patch S sub I would be approximated by this one. So the force on that patch dotted with the normal vector of the patch multiplied by the surface area of the patch. So that is the flux on each small patch. So we then add all the flux across all patches and to make an approximation for the total flux. So sum up all of this for all patches for all I, And if we want the approximation error to vanish, we simply allow the number of patches s sub i's to approach infinity. In such a way, of course, that the deltas here approach zero. So if the limit on the right hand side exists, then we can now write it, or uh, as a convention, we can denote it by an integral. So limit summation is integral. So we write it out as the surface integral of f dot n. So f dotted with n d sigma. So of course, next question is, how will we evaluate such integrals? By the way, this is usually called the surface integral of f dot n, or sometimes also denoted or sometimes called by the flux integral of f across S. Okay. So next, how will we evaluate the flux integrals? Of course, since our integrand f dot n is a scalar field, we may adopt the formulas from the last section in order to integrate it or to evaluate it. So we have D to be the projection of our surface onto the plane of integration, and we'll have two cases. First, if S has the Cartesian equation z equal to g of xy, then we'll be using this normal vector here, and we'll replace d sigma by this coming from from a previous lesson, and plugging all of those onto our integral. Our flux integral f dot n over s can now be written out as a double integral over this region d here. F can now be written out as a function of two variables, xy, and z is equal to g of xy, dotted with n. Then d sigma here would be this, and notice that the square roots here would cancel out, leaving this one, double integral of f dotted with this negative g sub x, negative g sub y 1, and integrated over dA. So next, if S is a parametric surface, it's parametrized by, let's say, R of uv, then we can get n to be Ru cross Rv over its norm. And again, based on our previous lesson, d sigma would be replaced by this one. So plug in all of this again here. F can be written out as f of R of uv. So it's a function, or it's parameterized by two parameters, dotted with n. Okay, ito. Then we have this sigma, this one. And notice again that the norms would cancel out. So, okay, they would cancel out. Okay, so just to summarize the previous slide, we have the following two formulas in transforming the flux integral into a double integral. The first formula is when the surface has a Cartesian equation. It's given by z equal to g of xy, whereas the second formula, or the second uh, method, uses parametrization for our surface. So our surface S is parameterized by R of uv. So let's try to solve some examples using these two techniques. Okay, so first, let's try to compute for the flux of F given by x, y, 2z across our surface S, parameterized by R of uv equal to u, uv, v, with u having values from 0 to 2 and v having values from 0 to 1. So since S is parameterized, we'll be using this form for the flux. So first, I will get R sub u. R sub u is 1, v 0, and R sub v would be 0, u 1. And get the cross product between these two, we get the cross product to be v negative 1 u. Next, our flux is the surface integral of f dot n d sigma over our surface S, which by this second technique can be written out as the double integral of f, written in terms of u and v, dotted with Ru cross Rv dA. So what is f? Well, f of u, uv, v, which is with this one, x would be replaced by u, y is replaced by uv, and z is replaced by v. So 2z would become 2v. And after that, we just get the dot product between these two vectors and try to integrate this with respect to first u, then v. So, okay, in this case, we have cancelled out uv, so we can easily simplify it as the integral from 0 to 1 of the integral from 0 to 2 of 2uv du dv. And in this case, we can write it out as the product of two single integrals, which you could easily evaluate having the flux to be equal to. Okay, next, we want to find the flux of f across the portion of the surface S, which is a cone, given by this equation z equal to the square root of x squared plus y squared, meaning you have the upper lip of the cone with its vertex at the origin, but we only want the portion of that cone between the planes z equal to 1 and z equal to 4. So we truncate the cones using these two planes. So here, the surface is given by its Cartesian equation, z equal to the square root of x squared plus y squared. So we can use the first technique. So solving for, so we have z equal to g of xy. G of xy is equal to this square root here. We get the partial derivatives. So verify that the partial derivatives of g with respect to x is indeed x over the square root of x squared plus y squared. And the partial derivative of g with respect to y is equal to this one. Then we proceed by using this. The flux is equal to the double integral of f at evaluated at x, y, z replaced by g of xy dotted with this vector negative g sub x, negative g sub y, and then 1. Then integrated over small patch a. So what is f of xy g of xy? Well, using this, you have negative 2x, negative 2y, then z is just replaced by g of xy. So we have this vector for f. Then substituting g sub x and g sub y here, we get this vector here. Then getting the dot product, we have this, which we could easily simplify. 2x squared plus 2y squared over the square root. You could easily cancel out the square root of x squared plus y squared. Then add to it this another square root. So this integrand can be simplified as 3 times the square root of x squared plus y squared. So ultimately, we have the flux to be equal to the double integral over d, where d is the projection of our surface onto the xy plane. So our integrand is 3 times the square root of x squared plus y squared dA. So, of course, looking at the integrand, it will be a little hard to integrate using rectangular coordinates dx dy, dy dx, or whatever. So in order to integrate this, hopefully by transforming it into polar coordinates, we'll be having an easier time integrating such integral. So looking at d, so once again, d is just the projection of s onto the xy plane. So it's truncated by z equal to 1 and z equal to 4. That implies that d is just the disk or the region bounded by the circles x squared plus y squared equal to 1 and x squared plus y squared equal to 16. So that is the region between two circles having radius 1 and radius 4. So the integral now in polar coordinates would have the following form. So 3, then the square root of x squared plus y squared is replaced by r. Of course, dA, as we know, it will be replaced by r dr d theta. Then looking at this region D here, r would run from 1 until 4. And since we have one complete revolution, uh, theta would run from 0 until 2 pi. So this one you could easily integrate. This is just 3r squared. Integrate with respect to r, get r cubed. Then okay, we evaluate it using or by separating it into two integrals. So we multiply these two single integrals, eventually getting the flux to be equal to 126 pi. Okay, so this would be our last example for this lecture video. So again, we want to find the flux. of this three-dimensional force field F, or sorry, velocity field F, which is constant. It's equal to the constant vector negative 1, 0, 3 across the portion of the cone given by this that lies inside the cylinder have equation x squared plus y squared equal to 1. Okay, so this is how our surface looks like. So we have the cone, upper nape of our cone, then we have the cylinder. So the part of the cone inside the cylinder would just be this one. Okay, so on the right, we can see this truncated surface, and D here would be the projection of this surface onto the xy plane. So obviously, you can see that the projection is just the disk centered at the origin with radius 1. So since we are given the Cartesian equation of our surface S, we shall use the first technique. Okay, so compute for g sub x and g sub y. So this is g. Again, g sub x and g sub y are given as such. Then plug it here. Then f, well, we don't have a problem with f because it's just constant. So we just replace this one by negative 103. So the flux can be written out in this manner. So we have a double integral over this region here of our velocity field f dotted with this vector. So we just substitute these values here and we'll get the following. Then do the dot product. Eventually we'll get this one. So we shall write this one as the sum of two double integrals. Okay, so we split it into two parts. So to find the flux, we just compute each double integral, starting with this one, second integral. Okay, so the second integral, the double integral of 3dA over the region D, geometrically speaking, is just equal to thrice the area of D. Since D is just a disk centered at the origin with radius 1, its area is just equal to pi times 1 squared, or pi. So thrice that would give us 3 pi. So what remains for us to solve would be this integral here. The double integral over d of x over the square root of x squared plus y squared dA. So just like what we did with the previous example, we'll be integrating this one using polar. So transforming the following into polar coordinates, we have it as such. X is replaced by r cosine theta. The square root of x squared plus y squared is just r, and dA would be replaced by r dr d theta. And since d looks like this, r runs from 0 until 1, and theta would run from 0 to 2 pi. Okay. Then r here would cancel out, and you could write r cosine theta as r times cosine theta. So you can separate this double integral and write it out as the product of two single integrals. The integral from 0 to 1 of r dr multiplied by the integral from 0 to 2 pi of cosine theta. So this integral here is equal to r squared over 2, which we evaluate from 0 to 1, giving us 1/2. And the integral of cosine theta will just be sine theta, which we evaluate from 0 to 2 pi, and that gives us a value of 0. So 1/2 times 0 is simply 0, meaning that the total flux of F across our surface S is 0 plus 3 pi, or simply 3 pi. So there you have it. So this is the end of today's lecture. I hope you guys have learned something from this, and remember that we have another discussion video for this lecture, and on that video more examples will be solved. Thank you for your time and patience. Bye for now.